welcome to the deep dive. If you're trying to make sense of that tidal wave of information flooding your inbox, well, you are in the right place. Today, we are opening up the essential toolbox for really understanding data, the foundational concepts of descriptive statistics. This isn't just about, listing definitions. Our mission here is to get a fast, clear grasp on how professionals turn all those raw numbers into knowledge that actually drives decisions. We want to know not just what the calculation is, but why. Why wouldn't analysts pick one method over another when the stakes are high?
That's it, that why. It's everything. Descriptive statistics at their core just help us understand the data we already have by summarizing its key features. We're basically distilling the essence of something complex into four main ideas: where the data center is, how much it varies, what its overall shape looks like, and whether two variables seem to be linked. It's the basic reporting language for data.
Okay, so let's unpack that. We'll start with this search for the average, then move into mapping the data's shape, maybe finding some of the weirdos, the outliers, and then we'll finish with what might be the most misinterpreted measure of all: correlation. All right, let's jump right in. Section 1, the many faces of center and spread. Now, when most people think center, they just think of the mean, the standard average.
Right. It's democratic. Every single value gets a vote, so to speak.
But the mean is also fragile, isn't it? It can be really sensitive to extreme values.
Oh, absolutely. Which is exactly why the median is so critical. The median, or Q2, is just the absolute middle number when you line everything up in order. It's the 50th percentile. Half the data is above it, half is below. Simple as that.
So let's make this real. If you're looking at housing prices or salaries, why do you almost always see the median price quoted in serious reports, not the mean?
Well, because they want to avoid that skew we were talking about. Imagine you have 100 regular homes in a neighborhood, and then someone builds one $50 million mansion. The mean home price is going to rocket up. It'll look like the whole neighborhood suddenly got much, much richer. But the median, it barely budges. It gives you a much truer picture of the typical home value. It's just more robust when you have those crazy outliers.
That makes so much sense. So the choice between mean and median is actually a strategic one right out of the gate. Our material also mentions a few others, like the mode, the most frequent value, and then these more niche ones, the mid-range and the mid-hinge.
Yeah, they have very specific applications, but for most day-to-day work, it's really the mean and median doing all the heavy lifting. But, knowing the sender is kind of useless without knowing the context, and that context is variability.
Right, a center point doesn't help much if all the data is scattered to the winds.
Exactly. So we start measuring that spread with the simple stuff: the range, which is just the max minus the min, and the interquartile range, or IQR. And the IQR is key because it's Q3 minus Q1. It tells you the range that contains the middle 50% of your data. A small IQR means your data is really tightly clustered.
But the real star of the show for spread is the sample standard deviation, right? And its parent, the sample variance.
That's the one. It tells us, on average, how far each data point strays from the mean.
Okay, and here's where we hit a small but really critical detail. When pros calculate the sample variance, they divide by n minus 1, not just n, the total number of observations. Why? Why that little adjustment?
This is such an elegant piece of statistical thinking. It turns out that if we just used n, our sample variance would consistently, systematically, be a little bit smaller than the true variance of the whole population.
So we'd be underestimating the real-world spread.
We would, every time. By subtracting 1 by using n minus 1, we make a tiny correction. It bumps the sample variance up just enough to make it an unbiased estimator of that true population variance.
Wow.
It's the essential step if you ever want to use the data you have to make conclusions about the data you don't have. It's the door from just describing to actually predicting.
So that tiny mathematical tweak is what lets us scale our knowledge into predictive confidence. That's a huge insight. Okay, so we found the center and the spread. Now we need to know what the whole data set looks like, its shape. Which brings us to section 2. Skewness.
Skewness just tells you if your data is piled up neatly in the middle or if it has a long tail dragging off to one side. If it's perfectly symmetric, skewness is 0. And crucially, the mean and the median are the same.
But the real world isn't usually symmetric. Thinking back to that salary data, a few huge CEO salaries would pull the whole picture, right?
Exactly. When data is skewed, right, or positively skewed, those big positive outliers pull the mean up higher. So the mean ends up being more than the median. The tail stretches to the right.
And I'm guessing the opposite is true for skewed left.
You got it. Negative outliers pull the mean down, so the mean is less than the median. Just by comparing the mean and median, you get an instant gut check on your data's shape.
And the analysis even gives us a rule of thumb.
Yeah.
A highly skewed right distribution, like maybe medical costs, could have a skewness value over 1.0.
Right. And once we get the shape, we need a way to locate any single point within it. And for that, we have the z-score.
The GPS for data.
That's a great way to put it. It's the standardized value. The z-score tells you precisely how many standard deviations a data point is from the mean. Negative z-score, you're below average. Positive, you're above. 0, you are the dead center average.
Let's use that class size example. Mean class size is 44, standard deviation is 8. So if a new class has 32 students, that feels small, but how small is it really?
Well, we run the z-score. A class of 32 is 12 students below the mean of 44. You divide that 12 by the standard deviation of 8.
And you get a 1.5.
Exactly. So that class is 1.5 standard deviations below the average. And the beauty is that minus 1.5 means the same thing relatively, whether you're talking about class size or stock returns.
That standardization is so powerful, and it lets us move right into Section 3, the empirical rule in detecting outliers. This rule, the 68, 95, 99.7 rule, feels like a magic trick. But it only works if the data is roughly bell-shaped or normal.
It's powerful because it gives you predictability. It says about 68% of your data will fall within 1 standard deviation of the mean, 95% within 2, and 99.7%, so pretty much everything will be within 3.
The classic example is SAT scores. If the mean is 1,500 and the standard deviation is 300, the empirical rule tells us instantly that 95% of students score between 900 and 2,100.
Right. You immediately know the boundaries for 19 out of every 20 test takers without any heavy math.
And this same logic helps us hunt for those weirdos, the outliers.
It does. The first method is simply using the z-score. Statistically, any value with a z-score less than -3 or greater than +3 it's a red flag. It's in that tiny 0.3% of the data.
So wait, you're saying if a data point is that far from the average, we should stop and ask, is this an error or is this just a really, really rare event?
Precisely. It's a flag, not a conviction. And the other key method for this is the box plot, which is a visual of the 5-number summary.
Minimum Q1, median Q3, maximum.
Yep. And the box plot gives us another quantitative test using that IQR we talked about. It sets up these fences. The limits for what's considered normal are 1.5 times the IQR below Q1 and 1.5 times the IQR above Q3.
So we're basically building a boundary around the middle 50% of the data. Anything that jumps that fence is a potential outlier.
You've got it. In the monthly salary example from the source, the upper limit came out to $6,276.25.
And one salary was recorded at $6,325.
And because that value is outside the fence, the box plot method flags it as an outlier. It demands you investigate why that one salary is so high compared to everyone else.
Perfect. Okay, let's switch gears for Section 4. We're moving from describing single variables to asking, are two variables dancing together? Measures of association.
We start with covariance. It tells you the direction of a linear relationship. Positive covariance, they tend to move together. Negative, they move in opposite directions.
But covariance is kind of messy, isn't it?
It's
Its value depends on the units you're using. So you can't really compare the covariance of, say, sales in dollars to temperatures in Celsius.
That's the problem. And that's exactly why we normalize it into the correlation coefficient, or it's unit-free, and it's always between -1 and +1.
And this is the number that business people live and die by. A value near plus or minus 1 is a strong linear relationship. Near 0 is weak.
And those rules of thumb are really handy. Anything over 0.7 in absolute value is generally considered strong.
But, and this is a big but, correlation only measures the strength and direction of a linear relationship. It doesn't tell you the slope, and it completely misses more complex patterns.
A crucial distinction.
So let's bring in the San Francisco electronics store example. The manager wants to know if TV commercials on the weekend are related to weekly sales. They run the numbers, and the sample correlation is 0.93.
A correlation of 0.93 is, that's incredibly strong. It's a very clear, powerful, positive signal. Descriptively, it's telling you that when ad spending goes up, sales track upward very, very tightly.
So manager sees 0.93 and thinks, that's it, we found the magic formula. Buy all the ad slots.
Of course they do. But that leads us right to the single biggest warning label in all of data analysis.
Okay.
Correlation is not necessarily causation.
There it is.
This is where descriptive stats can be so dangerous. Just because two things move together perfectly doesn't mean one is causing the other. We call them spurious correlations. Maybe a third factor, like a holiday weekend, caused both to go up.
So if that manager invests millions based purely on that descriptive 0.93, they could be making a massive mistake if the real cause was, I don't know, the weather.
A massive, expensive mistake.
So to recap, we've covered the whole toolkit. Finding the center, that crucial N1 adjustment for spread, mapping shape with skewness and z-scores, finding outliers and measuring relationships with correlation. These tools really do let you cut through the complexity and get a quick handle on any data set.
They do. They summarize what we know based on the data we have, but that gap, the one between a description and a decision, that can be huge. We found that super strong 0.93 correlation for the electronics store.
Right. So what does that really mean for the manager with a limited budget?
Well, since acting on that 0.93 correlation could lead to a very expensive decision buying millions in advertising, the provocative thought we want to leave you with is this. Knowing what you know now, that 0.93 is just a descriptive number, how much confidence should you place in it before you demand a more complex causal study to find the true effect?
And that really raises the essential question of where descriptive statistics end and where the heavy lifting of inferential statistics has to begin.